Okay, here we go. We are going to talk about acids and bases. You've done a little bit of research, done a home lab, and done some card game. Now we're going to talk to a lecture. Acids are sour, like a lemon. Bases are bitter, like soap. So if you were to taste them, that's what they would taste like. Now, it's not always a good idea to taste acids and bases, but we do eat some acids and we do eat some bases. What are some strong acids and bases? What does strong mean? Well, strong means 100% ionization. In other words, it 100% goes to its ions. Sort of like that dissolution lab we did with sodium chloride where it went to Na plus and Cl minus. It means 100% goes to its ions. So that's what strong means. Okay. Weak means only 1 to 5% go to its ions. The rest stay as a whole. So we've got strong, that means 100% ionization, and weak, that means only 1 to 5%. Now for our strong acids, we're going to look at our strong acids, and there's 6 strong ones that you need to remember. You got to remember them. And there's actually a swooping down that I'll show you here in just a second on the periodic table that helps you. There's 3 oxyacids, meaning acids that have oxygen: nitric acid, sulfuric acid, and perchloric acid. Sometimes chloric acid is also included here, but we're just going to talk about these 3. And then there's 3 binary: hydrochloric acid, hydrobromic acid, and hydroiodic acid. So let me stop here and go out to periodic table. When I talk about the swooping down, I'm talking about here to here to here. These are our 3 that make our oxyacids. The nitrogen combines with hydrogen and 3 oxygens to make nitric acid. The sulfur combines with 2 hydrogens and 4 oxygens to make sulfuric acid. And chlorine here combines with 1 hydrogen and 4 oxygens to make perchloric acid. So 3 oxygens, 4 oxygens, 4 oxygens. That's our swoop. That's our oxyacids. And then HCl, HBr, and HI are binary acids. HCl, HBr, and HI. So here's our swoop. Our swoop is our oxyacids. So swoop 3, 4, 4 with the oxygens, and then start here again without the oxygens and going down. All right, let's go back to the PowerPoint. Make sure I get the right one up. All right, and we're going to start from where we were at. So we've got our 3 oxyacids again and our 3 binary. We also have 6 strong bases that we're going to worry about. There's also some others that are strong, but these are the 6 strong ones that you are going to be responsible for: lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. You can get these from a Tetris pattern on the periodic table. So let's go back to the periodic table again. And if we look at lithium, sodium, and potassium put with hydroxides, shift over to calcium, strontium, and barium, that's where we get our Tetris pattern. Okay, can you see the Tetris pattern that occurs here? The first column combines with 1 OH, the second column with 2 OHs. Make sure to put the parentheses around the OH and put the 2 on the outside. Okay, we're going back. So hopefully this diagram that I'm going to give you will help you to understand the different levels of acid. There's several different descriptions. The stronger ones are in the center. It's sort of like a bullseye, okay, and the weaker ones as you go out. So the first one we talk about is called Arrhenius. And Arrhenius defined an acid as something that donates a hydrogen, and a base something that donates a OH. So that's pretty easy. If it loses a hydrogen, it's an acid. If it loses an OH, it's a base. Out a little bit farther from that is 2 guys that got together. Their names are Bronsted and Lowry. And they said, that's great, but it doesn't cover all of them. We have some acids that donate a proton. Doesn't necessarily have to be a hydrogen. Most of the time it is, but it doesn't have to be. So it donates a proton, and a base accepts the proton. So Bronsted Lowry, think of an acid's going to give the H+, and a base is going to accept an H+. And we'll talk about examples here in just a minute. Let's get just the bases down. The last one going out is our Lewis. Now you know Lewis from already doing Lewis dot. Well, guess what? It has to do with the dots again. So we have to look for unshared pairs of electrons. If it has an unshared pair of electrons that it can accept, in other words, it has a hole or an opening that it can accept those two pair of electrons, then it's an acid. If it donates a pair of electrons, then it's a base. Okay, great and wonderful. We've got the definitions down. Let's see how they apply. So, here's some examples. If I'm looking at Arrhenius, now remember Arrhenius acid is donating an H plus, and base is donating an OH minus. So if I look at a reaction like this, I can see this would donate a hydrogen. This would donate an OH. I get a salt and I get water. So we're still doing a double displacement reaction, but we always get water and we get a salt. Arrhenius acid-base reactions always are called neutralization reactions because they neutralize the acid and base, and I get a salt and water. Okay? These are the strongest types of acid-base reactions. It's also known as a strong acid, strong base, or neutralization reaction. The second type that we talked about was Bronsted-Lowry. And Bronsted-Lowry, remember, its definition was an acid will donate a hydrogen and a base will accept it. So here's an example. We have HF, which is a weak acid. We have water, and HF will donate the hydrogen, making water become a hydronium ion. Notice on the acid-base Bronsted-Lowry, we end up with charges. That's a clue to let you know that's a Bronsted-Lowry. We have also, if we start with an acid here and a base here, because we have to have an acid and a base, and water can act as either an acid or a base, because remember it's HOH, we label it like this. Over here, HF acts as an acid, but on the other side, it doesn't have a hydrogen to donate. So if I turned this equation around and went backwards, then the F minus would accept a hydrogen. So it becomes a conjugate base. Water accepted a hydrogen coming this way, but if we were to turn the reaction around, it would donate the hydrogen. So it becomes a conjugate acid. So Bronsted-Lowry has conjugate acids and conjugate bases. Just think of going backwards. So that's a clue for Bronsted-Lowry. The last one we talked about was Lewis acid and base. And on Lewis acid and base, remember it had to do with the electrons, the Lewis dot. So if we look at BF, B has only 3 electrons around it. So it can only fill 3 of its orbits. Well, this fluorine comes around and it has electrons to donate. So it makes room here and has that other fluorine come on, and we get this. So if you'll notice, it's sort of like a synthesis reaction. So Lewis acid bases, they come together and make one thing. They're very weak. Okay, they just come together and sort of help each other. All right. So there's the examples of the 3 different types of acid bases. Remember, Arrhenius, donate a hydrogen, acid. Donate an OH, base. Bronsted-Lowry, donate a hydrogen, acid. Accept a hydrogen, base. And you've got your conjugate base and conjugate acid. Lewis acid base has to do with Lewis dot. If it has room to accept an electron pair, then it's an acid. If it has an electron pair to donate, it's a base. So let's go on. Some acids can donate more than 1 proton. A monoprotic acid only has 1 proton to donate. So that would be like HCl, HBr, HF. If it has 2 protons to donate, it would be like H2SO4 or H2CO3. If it has 3, then it would be like phosphoric acid, H3PO4. So monoprotic, diprotic, triprotic. If it has many more, and these are often organic acids, which are long and nasty and horrible, they're known as polyprotic. Many hydrogens that it could donate. Okay. We have also what's called amphoteric compounds. These are compounds that can act as either an acid or a base. Water is an example because it's HOH, so it can donate a hydrogen or it can donate an OH. It can act as an acid or base. This one, HSO4 minus, it could accept a hydrogen becoming H2SO4, or it could donate a hydrogen becoming SO42 minus. Same thing here. I could accept a hydrogen becoming H3PO4, or I could donate a hydrogen becoming HPO4 minus 2. We have a lot of acids that come around in acid rain. We talk about sulfates. Sulfates are usually given off when we burn coal, and we end up with sulfuric acid when it combines with water. We have sulfates and sulfites, nitrates and nitrites. When they combine with water, give us nitric acid and nitrous acid. Carbon dioxide, when it combines with water, gives us carbonic acid, which isn't as strong as the others because it quickly breaks up again to water and carbon dioxide. Water self-ionizes. That means at any time when you drink some water, you're going to have some acid and base that you're drinking also. Now, we hopefully, with your card game that you played earlier today, found out that we had some things that were in common. If I have a neutral water, which is a pH of 7, then I have 10 to the minus 7 molar hydrogen concentration and 10 to the minus 7 molar hydroxide concentration. If I times those together, the Kw for that is the hydrogen concentration times the hydroxide concentration, which is 10 to the minus 14. That's all nice and wonderful, but we use a little chart here that helps us out. So we can go from pH to concentration of hydrogen to concentration of hydroxide to POH back to pH. Now I usually don't use this bottom one. I usually go up and around because it's a lot easier to subtract a number from 14 to get back and forth from POH, and then just put that number to the minus to get the concentration rather than have to deal with this. But you can use all of them. You can go all the way around depending on how you feel. Now, acids are usually on a pH paper, red, and bases are blue. And in between, you get the in-between number. So you should be picking up a paper that's like this that you can use. Now, these are important equations. Hopefully you came through in your card game. Kw, concentration of hydrogen times the concentration of hydroxide equals 10 to the minus 14. pH minus the log of the concentration of hydrogen. POH minus the log of the concentration of hydroxide. pH plus POH is 14. Concentration of hydroxide is equal to 10 to the minus POH. And concentration of hydrogen is equal to 10 to the minus pH. So these are all on the card that you picked up today after you did your little card game. So make sure that you have those handy because they'll be really helpful. You've got a pH scale, 14 being the most basic, 0 being the most acidic. Now we actually have things that are lower than 0 that are extremely acidic. But you can sort of see what happens at each one. Some things that you were testing at home on your pH scale. And here's another scale that you can look at. Okay, so hopefully you made your own little scale from your lab, and now you have got the equations that you can finish that lab up. A lot of things that we eat, a lot of things that are food, you'll notice are in the acid side. Okay, we usually don't eat anything that is above 7. We don't eat human blood. Baking soda only if our stomach's upset, or milk of magnesia only when our stomach's upset. Most of the stuff on the base side, what is it? Cleaners. Okay? So let's do a problem. If we're given a pH of 4.5, what is the concentration of hydrogen and hydroxide, and what's the POH? First thing I do is take, since I know that 4.5 is less than 7, it's an acid, and I can take that away from 14 and find out the POH is 9.5. And then I can quickly find the hydrogen concentration by taking 10 to the minus 4.5 and putting it in my calculator, and that's what I'll get. And the POH by taking 10 to the minus 9.5, and there's my hydroxide concentration. Real quick and easy, real fun, easy to do. So example 2, same thing, only this time I'm given the concentration of hydroxide. So it's harder to figure that out if I don't do minus the log of it. Oh, it's 7.27. That's a base, barely. Take it away from 14, get the pH. 10 to the minus pH gives me the concentration of hydrogen, and you can see. Now, we're going to stop here for a second, let you work on some problems, let you work on the finishing the lab, and then we'll come back together in just a minute.